Welcome to Day 5 of Math 111. Today we're going to be looking at some problems that are in the textbook. We're going to approach these problems using some of the strategies for solving problems that we have encountered in the course. This first problem comes from page 48, problem number 9 in the textbook. Alice Gardiner likes to play number games with the students in her class, since it improves their skill at both mental arithmetic and critical thinking. Solve each of these number riddles she gave to her class. She's thinking of a number. And here are the clues. The number is odd. It is more than 1 but less than 100. It is greater than 20. It is less than 5 times 7. The sum of its digits is 7. It is evenly divisible by 5. What is the number? Is more than one answer possible? So we have a number of clues here, and we want to try to use all of those clues to determine what the solution is to this problem. The second statement in the clues helps us a little bit. It is more than 1 but less than 100. Because of that clue, we will start with a chart listing all of the integers from 1 to 100. I've kept the clues here so that we can refer to them as we continue to work through the problem. Let's look at the first clue in the list. The number is odd. That means that we can eliminate all of the even numbers. All right, you remember what the even numbers are: 2, 4, 6, 8, 10, and so on. These are all of the numbers that are divisible by 2. So as you can see here, I'm scratching out all of the numbers that are divisible by 2. In this array, they occur in columns. So I'm just simply marking out the columns that are not going to be used. Let's continue now. The next clue is it is greater than 20. So that means I can eliminate all of the integers that are not greater than 20. So the remaining integers that are less than 20. I'm going to mark those out. You can see here that I've marked out all of the integers in the first 2 rows now. The next clue, it is less than 5 times 7. 5 times 7 is 35. Since our mystery number is less than 35, I can eliminate all of the integers that are 35 and greater. So I'll mark them out now. You can see now that I've marked out all of the integers that are 35 and greater. So there are just a few left to be considered. The next clue is the sum of its digits is 7. So I can look at the remaining numbers. I've got 21, 23, 25, 27, 29, 31, and 33 left. All I have to do is add the digits in each integer and see which one sums to 7. I'm marking out the ones that do not work. 21 does not work. The sum of the digits is 3. 23 is eliminated because the sum of the digits is 5. The sum of the digits of 25 is 7. I'm keeping it. 27 has a sum of 9. 29 gives me a sum of 11, which is too large. 31 and 33 are both too small. Their sums are 4 and 6. So 25 is the number that's left. And this last clue, it is evenly divisible by 5, gives me a clue to check my solution with. 25 is evenly divisible by 5. So going back to the original question, what is the number? Is more than one answer possible? So we now know that the answer is 25, and we do not have any more possible solutions. So 25 is the only possible solution. The next problem is found on page 48 in your textbook. This is problem 14. Saturday afternoon, Aaron, Boyd, Carol, and Donna stopped by the soda fountain for treats. Altogether, they ordered a chocolate malt, a strawberry milkshake, a banana split, and a double-dip walnut ice cream cone. Given the following information, who had which treat? We have 4 bits of information here. Both boys dislike chocolate. Boyd is allergic to nuts. Carol bought a malt and a milkshake for Donna and herself. Donna shared her treat with Boyd. So we have all of this information, and we need to organize it in some way that we can determine what our solution is. One approach to working a problem like this is to organize the information in a table. Once you have the table set up with the information, you can begin eliminating choices that cannot be a solution. So notice in this table that we have the names of each of the students, and we have the choices that they have. So the first clue is both boys dislike chocolate. So we know that Aaron and Boyd did not order a chocolate malt. So I'm going to put an X under chocolate malt beside their names. Boyd is allergic to nuts. So we know that he's not going to have the dessert with the walnuts in it. So we'll also put an X beside Boyd's name in the column for the double-dip walnut ice cream cone. Carol bought a malt and milkshake for Donna and herself. So Carol and Donna are having the malt and the milkshake. That means they are not having the banana split and the double-dip walnut ice cream cone. So we'll put X's in the columns for banana split and the ice cream cone beside Carol and Donna's names. That fourth clue, Donna shared her treat with Boyd. Okay, so we're going to go back and see what it is about Boyd. Boyd is allergic to nuts. So we know now that Donna did not share her treat with Boyd. That means that she's not getting the double dip ice cream cone. After we've eliminated things that the students cannot have, we can start looking at what's left, and it's a lot easier to figure out what the solution is. There's only one person who could get the double dip ice cream cone. That would be Aaron. Since the girls had the chocolate malt and the strawberry milkshake, then that means Boyd would have had to have the banana split. We're told that Donna shared her treat with Boyd. Boyd doesn't like chocolate. So that means Donna would not have had chocolate, the chocolate malt. So Donna would have had the strawberry milkshake. And then that leaves the chocolate malt for Carol. So we summarize what we have found here in a sentence Aaron had the double-dipped walnut ice cream cone. Boyd had the banana split. Carol had the chocolate malt. Donna had the strawberry milkshake. The next problem comes from pages 47 and 48 in your textbook. This is problem number 7. Josh wanted to buy a bicycle but didn't have enough money. After Josh told his trouble to Sam, Sam said, "I can fix that. See that fence? Each time you jump that fence, I'll double your money. There's one small thing, though. You must give me $32 each time for the privilege of jumping." Josh agreed, jumped to the fence, received his payment from Sam, and paid Sam $32. Repeating the routine twice more, Josh was distressed to find that on the last jump, after Sam had made his payment to Josh, Josh had only $32 with which to pay Sam, and so had nothing left. Sam, of course, went merrily on his way, leaving Josh wishing that he had known a little more about mathematics. The question is, how much money did Josh have before he made his deal with Sam? I encourage you to read problems like this multiple times and try to develop a plan for solving it before you start writing something down. This problem is a little bit complicated, so it's important that you apply Polya's first principle, understand the problem. On this slide, I've repeated the important information that helps us get through parts of this problem. Each time you jump that fence, I'll double your money. There's one small thing, though. You must give me $32 each time for the privilege of jumping. And then he jumped the fence twice more. Okay, so that's important to us. We're going to work backwards on this one. This seems to be a logical approach. I've even set up my table backwards. So you'll notice in the table, my first line is last jump, and then the previous jump, and the first jump. We remember as we read the problem, he jumped the fence, and then it said that he repeated the routine twice more. So that would be a total of 3 jumps. Let's see if we can think through this and see how I set up the table. After the last jump, Josh had no money. He gave Sam $32. That's all that he had. Remember, Sam is doubling Josh's money, so $32 is twice what Josh already had. Half of 32 is 16. So Josh must have had $16 before he made his last jump. And when he jumped the fence, Sam doubled it. So he gave him $16 for a total of 32. Let's go to the previous jump. So after Josh made his payment, he had $16. He had given Sam $32. So before that, he had $48. Okay, remember, this is double the amount that he had because Sam gives Josh enough money to double his amount. Half of 48 is 24. So Josh would have had $24 and Sam would have given him an additional $24. So after the first jump, Josh would have been left with $24. Okay, remember he gave Sam $32. So before that, he would have had a total of $56. When he jumped the fence the first time, Sam doubled his money. So he would have had $28, which is half of 56, and Sam would have given him the other $28. So let's look at the question again. How much money did Josh have before he made his deal with Sam? He would have began this process with $28. This is the solution to the problem. This next problem is found on page 49 in your textbook. This is problem 19A. How many people must be in a room to be sure that at least 2 people in the room have the same birthday? Not birth date, but birthday. Assume that there are 365 days in a year. There's a special principle that applies to problems like this. It is called the pigeonhole principle. The pigeonhole principle states if M pigeons are placed into N pigeonholes and M is greater than N, then there must be at least 2 pigeons in one pigeonhole. We will let the days of the year be our pigeonholes. How many people must you have in order to guarantee that 2 people have the same birthday? So there are 365 days in the year. So in order to guarantee that at least 2 people have the same birthday, you must have, at minimum, 366 people. So if you think about this, you could have each person having a different birthday up to 365, and then that next person, person number 366, would have to duplicate one of the days that has already been used. So today we have looked at a number of problem-solving strategies. This last problem used the pigeonhole principle. We eliminated possibilities with the problem with desserts. We worked backwards with the problem dealing with Josh and Sam jumping the fence. So we've seen applications of a number of these strategies today. The other 2 are use a variable and algebra as a great explainer. So these 2 strategies would involve using algebra to solve your problem. Think about these examples, look at them again, and try to absorb what we have done in order to use these strategies in working these problems.